Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its products and experiences in supply chain optimization and sales and operations planning, S&OP. This video is confidential and may not circulate outside the receiving company without HI's authorization. Enterprise-wide optimization. A company's value chain is made up of two chains, which are strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. An example is this holistic view is oil enterprise-wide optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of HI Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detail the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. In 2010, HI executed the project The Hypothalamus of an Oil Organization. Challenge: design and implementation of a DSS decision support system. For the optimization of energy resource that links all stream of the supply chain petroleum products, with emphasis on the consumption and marketing of the energy used by the network. Solution: design and prototype implementation of the DSS that following models. Production of crude oil. Transportation of crude oil. Oil and biomass refining. Production and industrial services, and transport of refined products. Result: the model is the base to the formal implementation of the value chain model for a LATAM petroleum company. The models were delivered in prototype version, in the sense that the oil company did not have the database in the expected time. This is one of the most important projects developed by HI. Supply chain optimization. Today, and for several decades now, the traditional S&OP mathematical model is limited to planning production taking as border conditions, I, sales, 2, preventive maintenance, 3, financial budget, and 4, the workforce. According to the modernization of the S&OP process can be visualized as integrating multiple mathematical models that can be used individually, or integrated according to decisions, and/or studies supported by the DSS. Project: Bavaria Supply Chain Design. Challenge: in 1990, Bavaria hired HI to implement tactical and strategic planning optimization models, using 386-486 Intel CPUs, because its actual models does not run properly in its IBM mainframes. Solution: the models were implemented using the first version of the Bender's multi-level partition and decomposition methodology, that is part of the HI Optex Optimization Expert Robot. Result: Corporate Industrial Planning Decision Support System, PCSI, oriented to strategic and planning models. In 1998, PCSI made it possible to plan a beer supply chain of 18 production plants, 42 bottling lines, and more than 230 SKUs. The models have been used for over 25 years, primarily to support S&OP activities. Implemented in IBM OPL using IBM Plex. Project: Beer Supply Chain Optimization. Challenge: in 2014, SABMiller, Bavaria, hired HI to upgrade tactical planning optimization models, according to the state-of-the-art of information technologies. Solution: design and implementation of new models, to support S&OP process that includes the modeling of detailed process in the breweries and work shifts in factories. The new model includes detailed modeling of the area of breweries, work shifts in factories, product substitution, the assembly of combos in distribution centers, and reverse logistics of the processing of bottles and baskets. Result: Implementation of powered new mathematical models using IBM optimization technologies. Consulting Project, Global Supply Chain Design. Challenge: in 2024, a multi-Latin company hired HI to redesign its global supply chain, in order to determine how best to serve the Latin American and North American markets. Modeling involves the coordination of an international network of raw material plants and end product plants. Solution: applying the new HI methodology for the resilient design of global supply chains, including financial risk management. The model is called GSCD. Result: project in progress. The result will be the implementation and use of the GSCD to determine the best global supply chain for the multi-Latin enterprise. The Decision Support System, DSS, for design and planning of industrial supply chains will be called SCD. SCD must be made up of multiple models that interact with each other. Models may be solved in two ways. Coordinated, independent models that share results with each other, according to a logical data flow. Integrated, the models are integrated into a single mathematical model, that is solved as a single mathematical problem. The best way is integrated, considering that it can solve the holistic optimization model, until it reaches the optimal solution. The first model will be called LogFin. It is oriented to define the investments to be made in infrastructure necessary for production. It corresponds to a dynamic model that defines, for each period of the planning horizon, the investments to be made, and the network for short-term operation. As input parameters, it should consider the costs of investment, rate of return on capital, the costs of loans, payment period, and other financial considerations. Model constraints are related to investment logistics and financial risks. The main results of the model are NPV, net present value, of the investments, VAR, value at risk, cash flow, and network design for the first periods. The second model will be called SANDOP. It is aimed at simulating industrial operations for each possible network proposed by the investment model, LogFin. As input parameters, it should consider, at least, the forecast of demand of final products, raw material supply, operational costs, and sell prices. The model can be extended to consider other aspects such as technological innovation that affects the productivity of processes, new technologies, which may affect market prices, and others that are considered convenient. In general, all input parameters are uncertain, and it is appropriate to consider that this makes a stochastic programming model based on scenarios. This characteristic makes the LogFin model a coordinator of the evaluation of the scenarios to be considered in SANDOP. It corresponds to a dynamic model that defines, for each period of the planning horizon, the industrial operations, and the storages of materials. In certain cases, it may not be necessary to consider product storage, because it may have little impact on investment costs, and additionally, it may be considered that its offer is always provided by the market with stable prices. This is not the case for oil storage, where the market prices and the supply of oil and gas is uncertain with high volatility. The constraints of the model are related to the industrial production process. Normally, there are several alternatives to simulate this process. At one extreme, we may formulate a very simple model, perhaps a few aggregate equations, that synthesize the process. At the other extreme, we may formulate a detailed model that simulates the processes with great certainty. The decision is of the modeler. What is true is that the available computer technology, computers plus solvers, allows very advanced models in this aspect. Therefore, the level of detail will grow exponentially in the next years. The main result of the model is the operational simulation for each period for each scenario. Data that are necessary to evaluate the future cost function, that generate the decisions of the present. The third model will be called ALM. Its objective is to simulate the assets and liabilities management, ALM, considering the results provided by LogFin and SandOp models. ALM is a modeling consolidated methodology that focuses on the financial modeling of companies. Its growth is generated at the end of the past century, in the financial sector, as a result of the Basel Accords. The minimum ALM modeling should be oriented to evaluate the NPV, for a pre-established ROI, return of investments. It will provide the financial statements, balance sheet of assets, liabilities and equity, income statement, profit and loss, after tax, royalties, and other contributions, and cash flow. Extended ALM modeling may include investments in alternative assets and liabilities, payment of dividends, capital repatriations, capital flow, and multiple currencies. In healthy logic, this model must be the coordinator of the holistic investment process, since it is the financial vice presidencies of the organizations responsible for endorsing investments in production assets. The results of the holistic optimization process are probability distribution functions, for the primal variables, and the dual variables of all DSS models. For example, the NPV. In simpler modeling, these distribution functions are obtained using spreadsheet simulation models. The results are not comparable, because of the methodological difference in the approach. Refined Petroleum Production and Energy Services Planning Model. Challenge: to develop an integrated production and industrial services optimization considering that the optimal management of power of industrial systems implies a holistic position oriented to integrate the production planning of goods with industrial, energy, services that are consumed in the production plant, and finally integrate it with possibilities of self-production and negotiation of this energy in the energy markets. Solution: design and implementation of an optimization model that simulate the production process, and simulate industrial services process, like boilers, pumps, turbines, electricity plants, collector, compressors, etc. The approach considers that industrial processes have variable speed, and that the power consumption as a function of the speed is nonlinear, it is exponential. Service plant: place where various industrial operations, related to the auxiliary services demanded, by process plants are developed. Auxiliary service: essential services for the operation of any production system, they allow to guarantee the quality, and the continuity of the process, and service unit: facilities that make up the service plant, its function transform the different services to adapt them, to the requirements of demand for auxiliary services of the process plant. The main objective is to optimize the management of service plants, by considering the fluctuation of demand over time. The optimization of the two plants is carried out in an integrated model. Result: a prototype model that optimizes the oil refining process including industrial services plants at tactical level. A similar model implemented for the Petrobras Recap refinery, São Paulo, Brazil, achieved up to 10% cost reduction. It is part of the oil and gas artificial hypothalamus. The simultaneous optimization of both industrial production and energy conversion is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. HI may integrate complex industrial process models to redesign the power supply system, according to the new power technologies. This type of model includes the simulation of polluting processes to determine the optimal mixture of fuels, in accordance with environmental regulations. Research and Development Project. Challenge: to implement an optimization model that integrate the production with the financial modeling to permit the enterprises to implement optimization models for the integrated business planning, IBP, process to improve the decision-making process. Solution: design and implementation of an optimization model that connect financial, ALM, with supply chain planning, SandOp, models allowing to optimize Cash flow and treasury management. Working capital. Fiscal management, dividends, capital repatriation, payment/prepayment of liabilities. Capital and equity structure, and transfer prices. Based on stochastic programming framework, SANDOP ALM may include corporate financial risk analysis. Result: a prototype SANDOP/ALM model was developed by a high professional, as part of his postgraduate thesis in UPC, Universitat Politècnica Catalunya. Additional to the production/distribution variables, it produces financial statements, I, losses and gains, 2, cash flow and 3, balance of assets and liabilities. The model was applied to optimize transfer prices in a realistic beer global supply chain. Consulting project, distribution chain design. Challenge: implement an optimization model to design the customer's distribution chain. Products: pharmaceuticals, personal care and household hygiene, processed foods, and agriculture and veterinary. Solution: design and implementation of an optimization mathematical model to determine the services and facilities that optimize the national distribution network. The model includes inverse logistics process. Result: a MIP model that designs the national supply chain and simulates the operations. Optionally, the model may use stochastic programming approach, based on probabilistic scenarios for the parameters like demand, prices, and others. Project: decision support system for the optimization of a pharmaceutical supply chain. Challenge: implement tactical planning and scheduling models to optimize the pharmaceutical supply chain. Solution: implementation of a set of optimization models that integrate production planning and scheduling in plants. 2. Minimize machine times and format changes, optimize inventory policies, minimize the cost of handling raw materials, and maximize the level of customer service. The model includes work shifts in factories. Result: a DSS that integrates the following models: medium/short-term demand forecast, SANDOP tactical planning, inventories policies, global sourcing optimization, and scheduling production lines. The DSS was integrated with SAP ERP. Project: decision support system for the optimization of an auto part supply chain. Challenge: to implement a DSS that includes tactical planning and scheduling models to optimize auto part supply chain, mainly car seats. Solution: implementation of optimization models that integrate production planning and production scheduling at the production plants to minimize setup times and format changes in the machines, to optimize the inventory policies and raw material acquisition planning, and to maximize the service level. The simulation of the seat manufacturing process is detailed and includes substitute production formulas with different characteristics of the polymers, which impact the setting speed and temperature, which affects the service life of the molds. The mathematical model manages the service life and production of molds. Result: a DSS that integrates the following models: demand forecast medium/short term, SANDOP tactical planning, inventories policies, and scheduling production plants. Consulting project, hospital and surgical equipment supply chain optimization. Challenge: to solve the planning processes of hospital and surgical equipment and services in SLA, Spanish Latin America, Colombia, Mexico, Chile, Peru, Costa Rica, and Puerto Rico. Solution: design and implementation of a mathematical model for optimize the planning processes of hospital services of surgical equipment. It produces customer service policies and optimum inventory levels at each distribution center. Result: a consulting project, using the mathematical model, that proposed customer service policies that estimated a saving in CapEx for inventory of 35%, with respect to the policy plan before the study was carried out. Project: dairy supply chain optimization. Challenge: to implement tactical planning model, to optimize the supply chain, in the short-medium term, of a large dairy enterprise. Solution: implementation of an optimization model to support the SANDOP production activities, including the following type of products: beverages, milk, baby food, desserts, cheeses, cream and butter, and finesse products. The model includes work shifts in factories, and blending processes to prepare the base products. Result: an optimization model to support sand-op production activities. Project: ceramic supply chain optimization. Challenge: to implement tactical planning model to optimize the supply chain in the short-medium term for ceramic industries. Solution: implementation of an optimization model to support the sand-op production activities for sanitary ware. The model includes work shifts in the factories and a detailed simulation of the furnace. It also considers the process of selling and transporting products to different markets. Result: an optimization model to support sand-op production activities including the start, stop of furnace. Proof of concept: beverage supply chain optimization. Challenge: to implement a tactical planning optimization model oriented to beverages industries, soft drinks, waters, juices, etc. Solution: design and implementation of a sand-op optimization model for beverages industries. Result: use the mathematical model in a proof of concept for a large beverage company in Peru. Project: plastic supply chain optimization. Challenge: to implement tactical planning model to optimize to supply chain in the short-medium term for plastic health products. Solution: implementation of an optimization model to support the sand-op production activities that includes the following type: syringes, probes, etc. The model includes the work shifts in factories. Result: an advanced planning and scheduling system, APS, to support sand-op production activities. Research and development project: food supply chain optimization. Challenge: to implement a tactical planning optimization model oriented to food industries, pasta, jams, soups, etc. Solution: design and implementation of a sand-op optimization model for food industries. Result: use the mathematical model in a proof of concept for a large food company in Peru. Research and development project: textile supply chain optimization. Challenge: to implement a tactical planning optimization model oriented to textiles industries. Solution: design and implementation of a sand-op optimization model for textiles industries. Result: use the mathematical model in a proof of concept for a large textile company in Peru. Project: available to promise optimization. Production, inventory, and distribution models. Challenge: to implement an informatic tool to allocation of products to client orders, and delivery orders to trucks. Solution: implementation of design and implement an ATP, available to promise, optimization model, that finds the optimal allocation of products to client orders, and delivery orders to trucks. Result: an optimization model to support ATP activities. The solution is linked to its ERP and WMS to execute the next 15 dispatch plan days. For the first few days the model make emphasis in the customer service criteria. For the medium term, 2 to 3 weeks, the operations cost is the priority. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.